Have you ever wondered how secure your online information really is from hackers? Traditional encryption methods rely on the fact that trying to find factors for very large numbers is very difficult, and much like trying to find a needle in a haystack. But what if these numbers exhibit a pattern which may light up the path to success? Let's dive in to Shor's algorithm. We start with some random number a less than n and explore the remainder when a taken to the power of x is divided by n. This sequence, which we can write as f of x is equal to a to the power of x modulo n, where mod n means remainder when divided by n, will eventually show a pattern of remainders. Given that f of 0 is equal to 1, let's find the next term, f of t, when f of t is equal to 1. What we'll get is that the function will repeat after every t values, i.e. t is the periodicity of f of x. What is special is that a to the power of t minus 1, a multiple of n, is equal to a to the power of t over 2 plus 1 multiplied by a to the power of t over 2 minus 1. And notice that a to the power of t over 2 minus 1 cannot be a multiple of n, as that would require a to the power of t over 2 to be 1 more than a multiple of n, which would require f of t over 2 to equal 1, which cannot be the case as t is the smallest such integer where f of t is equal to 1. What this means is that there's a pretty high chance that a to the power of t over 2 minus 1 shares one of the common factors with n, helping us crack the factorization of n, as then we can compute the greatest common divisor of n and a to the power of t over 2 minus 1 to get one of the prime factors of n. In fact, if t is even and a to the power of t over 2 plus 1 is not a multiple of n, we are done, which happens about a third of the time. So finding t is really helpful, and while not possible to be computed on a classical computer efficiently, a quantum computer could compute all our powers of a at the same time, greatly speeding up the process. The only problem is that you get a single jumbled output for an answer, and you want to find specific patterns and trends within it, namely the periodicity. Fortunately, the quantum Fourier transform helps us out. Picture a cacophony of people playing various tunes simultaneously. It's difficult to distinguish individual melodies. We need a method to isolate one tune, much like using noise-cancelling headphones. The quantum Fourier transform separates the frequencies within the quantum output, isolating the desired tune, the periodicity of f of x, t. And with that, we have a revolutionary breakthrough in cryptography. Keep an eye out on your data.